Alright, let's begin with the Leetcode question, I guess. Let me just reset it. And yeah, let's start the timer and solve this one. Cool. What do we have here? Median is the middle value. In ordered integer list of the size of the list, there is no middle value. Median is the mean of two middle values. For example, alright, it's an ordered integer list. So what we have to do is basically, alright, insert these values into an array. Basically insert values in the array and find the median. Finding median will always be of O of one operation, which is constant time complexity, because it will be always from the mid elements, and adding a number in sorted way kind of O of n complexity, right? Alright, so we kind of have to optimize the addition of numbers into our into our data structure, whatever we will do. So what we need to have is, we always gotta have the mid value present with us if we need to make the median finding constant, right? Alright, so how do we do that? Say we have an array 1 2 3. These are the numbers which are inserted one by one. But get the mid value, right? For getting the mid value, okay, it will be like create a heap on priority queue basically. We gotta have the mid value, so it will be left and right. Right, so wait a second, got it kind of. And these priority queues, two priority queues to store our basically to add our numbers, which will be a O of log n operation, right? And yeah, log of n. So it's like we have a min q, min pq, and a max pq, right? What we'll be doing is, let's say we have 1 2 3, all right. We'll basically be storing all the left hand side numbers of the sorted list, which is the smaller numbers, into a max heap or a max priority queue, and the right side of the numbers of the list, or let's say the greater numbers, into a min priority queue. The reason for that is because we want to get the mid always. So mid of left hand side numbers will always be the maximum value, and for right hand side number it will be the minimum value. So cool. Left side will be max PQ and right partition will be a min priority queue. Cool. Got it. Let's write the comments. What else? We'll try to min heap dot size will be approximately equal to max heap dot size. Alright, the reason for this is if there are odd numbers, one of them will have a greater number, one of them's size will be one element greater, and if there are even numbers, both will be equal, so that we get the element from both of them, and then further proceed to divide them by 2 and get the median. Alright, cool. So how we proceed with storing this is somewhat interesting over here. Let's say I get a number 1, 2, 3. I get 1. Where do we store it? We store it in max heap. Push it in max priority queue. Right. Then we get 2. Push 2 in min priority queue because the difference can't be greater than 1. So here it is 1, over here it is 2. Then we got 3. We push 3 into max priority queue. Actually into min priority queue. Got it. What if we had 0 to push over here? What would be done over here? That's interesting. Huh. So we gotta have a conditional check, right? Basically by default, let's say we put it in our max heap, which is the left side of the queue. What if I receive 3? 3 is what? Greater than max dot peak. Then we'll put it in min heap. Right. Basically, if it is less than uh, the value that we are getting in max heap cut top, then only we'll put it inside this max heap. So it's kind of like this. We basically draw. Cool. This is a oops, max heap min heap. We got a list of numbers, which is let's say 1 is inserted first, then 2, then 3, then 0, then 4. Alright, pick these elements one by one. What we'll have to do is first of all we come to 1. The first value will always be inserted in max heap. First value. Basically if max heap is empty, push into max heap. These are the pointers that we need to keep note of. Next value comes 2, right? And 2 is pushed in min heap. Alright, so 2 will be pushed into min heap. Next value comes out to be 3. 3 again should be pushed in min heap. Now what's the logic over here? We think about it, max heap. Now 0 comes over here. 0 will be pushed into max heap. So basically if max heap is empty or num is less than max.peak, then push into max heap. Cool. When are we pushing into min heap? Else push into min heap. Alright, now one more thing that we need to keep in mind is here we have two elements, right? 4 comes over here. 4 is not lesser than this, so we put it over here into our min heap. Let's say the next number that we get over here is again 5, which is basically again, okay, pushed into what? It will again be pushed into min heap. Alright, now we need to keep a check over, since the size of this max heap is, okay, this is the next condition, that max if size difference is greater than 1, what do? We basically, okay, min heap, give me what, 0 1. We basically take min heap ka, what do you say, min heap ka peak and offer it to max heap, offer min heap to max heap. Okay, one thing is this. So what will happen over here is min heap ka peak is 2. 2 will be pushed into this. So it will be like 2 is pushed into this. Alright, now both of these have 3 elements. Let's say the next element is -1. Let's say we get -1 over here. -1 will be pushed into this one. Cool. Next element is what? -2. -2 is pushed into this one. Now this element, how many elements do we have here? 1, 2, 3, 4, 5. This is 3 again. If size of max heap is take the max heap, offer max heap dot peak to min heap. Right. This is what our condition is kind of as of now. That's what will help us. Alright, let's see. We'll have priority queue of integer Alright. Okay, what are the conditions over here? Oh, cool. Let's see what to do. Basically, if max heap is empty, if max dot offer num else num dot offer num. If what we do in this case is return okay speak that's where it needs this. Else if the size is greater, what do we do in that case? Whichever side has greater number of elements. If alright, let's see if this works. Hopefully it does. Alright, it did work for the first test case. Let's see if it works for the further test case. Oh great, it worked. Cool. It worked. That's great. Alright. What we did is really simple, I guess. Yeah, cool. It worked. That's great. Alright, let's see what do we have to do for fixing Kali verification. Thank you for your patience while we reviewed our submission for project. Okay. Demo videos does not show the OAuth consent screen workflow. Please refer to the attached screenshot. The provided homepage redirects to kali.msraga.dev/auth. Of course it does. Homepage that match is submitted in your cloud console. Great. A link to a demo video showing OAuth workflow. Alright, I gotta click on this. Cool, got it. Let's see what we have. Kali. Can I log in over here? Okay, I got it. Cool, I'll have to start it in local. Alright, give me a second. I guess I have to get the env file. Okay, it's fine. And dev. got it. This should work. Yeah, cool, it worked. Let's visit on localhost 5173. Cool. I guess I'll also start recording. All right. These are the services that I require access for on Kali. Basically, this lets me store the person's profile picture and user's name and email data on our DB level to create his or her account. This is basically what we require: their full name, profile picture, and any other thing that is publicly available so that we can store it in RDB level to create a user account. And definitely we need a primary email address for as a unique identifier in RDP. So yeah, and the next thing is we basically need the permission for users calendar events that we can either delete, edit, or share with others, because when a user sends the request, we have to schedule the same event. Let's say I sent a request to some other user and the other user accepted it, then we'll be creating the event in both the users Google Calendar. So yeah, that's why we'll be needing all these permissions. And if you see over here, I can send requests to other people through this page and they can accept it. So yeah, that's why I need these permissions. Cool. All right, let's see what we have over here. Cool. I gotta go in movies. This is not it. I recorded. Like, this is it. We basically need. Alright. Cool. Cool. Let's study about Cloudflare workers. Yeah. I guess what I'll be doing is, if I get a good hold of Cloudflare workers, I'll be most probably moving my Kali emailer service to Cloudflare workers instead of AWS Lambda, because I don't wanna pay bills to AWS Lambda if it is invoked. I know I get free requests on Lambda also, but yeah, I find it more fascinating. So I just want to explore Cloudflare workers, and if it's good enough, I'll most probably using these over Lambda, because what Lambda does is gives you in-house support for S3 buckets. Like the integration over there is really good because of the ecosystem. So yeah, I kind of don't need that S3 access over my serverless function or my emailer utility. So maybe we can move it over here just for exploring stuff. So yeah, let's read this. These are basically all the things I guess that we get on AWS also. Like this might be an alternate to SQS. Similarly, this is SQL database, serverless SQL database. This might be kind of like S3. So yeah, let's launch the playground and see how it works. Okay. What it does is index.js import welcome from welcome.html, export default params request envc takes as context, I guess. Yeah. How do you run it? Where do we get the option to run it? They get everything regarding the request. The method, the body, anything else that you get. Alright, so what it does is basically we need to export this default function. Basically we default this by export this async function, this fetch function. Exactly. Takes request environment ctx as default. Alright, so it's like one thing. Takes another minute. That's really huge. Okay, let's see what it has done. Next.ts, there you hit. Whole thing. Configuration is this. That's interesting. Let's do one thing. Let's recreate this actually. And right. Okay, what happened over here is not running. Always got it. Let me do it once again. Maybe. Right. It should log me in this time, I guess. Let's do. Okay. I just got logged in my browser. Why is it not logging in here? Ah, okay. Allow Wrangler to make changes to your cloud. Allow. And cool. This has worked. Would you like to register the workers.dev subdomain now? Alright. Alright, now it's basically cool, just waiting for the addition of DNS, I guess, right? Let's see, what do I have here? If you see, this should give me a subdomain for workers, which is workers.dev. Yeah, it has registered successfully. Okay, it's taking really long, I guess. Okay, it ran successfully. New project. Let's view the project. And this is the dashboard. Okay. This is the project link. Cool. I wanna do it over here. And this is of course not up yet. Here is that we had. Cool. What do we have in this index.js? It's nothing but JS, of course. Cool, this is what I need. Right. And I also need what package and JSON. I also need a resend basically. Resend. second, what is this? It's a TypeScript, right? Okay. Then I have to store my secrets over here, you're saying. Alright, I can directly put secrets like this. No worries, but why is it not? Alright, so basically the thing is that you can't run Node.js file systems or path module in Cloudflare workers because it is using a different environment other than Node.js to run your JavaScript or TypeScript basically. That's why I don't think it will be a good choice to run my emailer service over here. So yeah, I think I'll just move this file. Sudo or yeah, there we go. It doesn't exist now, and we'll basically workers are interesting actually. What is this color theme? Sort of red dark. Alright, I'll not use choose workers now then. Great. Cool. Let's do one more question, I guess. One more lead code. And yeah, I guess we can do one more lead code. Since I'm not deploying the candy emailer on Cloudflare workers because of the limitation of using Node.js on it. So yeah, I'll be solving one more lead code, I guess. The question is combination sum given an array of distinct integers candidates. The target integer target return a list of all unique combinations of candidates where the chosen numbers sum to target. You may return the combinations in any order. The same number may be chosen from candidates an unlimited number of times. Two combinations are unique if frequency of at least one of the chosen numbers is different. The test case generator says that the number of unique combinations that sum to target is less than 150 combinations for the given output. Okay. Got it. All elements of the candidates are distinct. Got it. So basically we have a target, we have a list of integers. What we want to do is make a combination of these integers which add up to the target. Great. So the list as of now is 2, 3, 6 and 7. What we need to do is start traversing from 0. Current sum is 0. Index is 0. If nums of I is less than target minus sum, we move ahead, we simply return. And if it is less than, then what we do is we add it in sum. And basically otherwise return. Right. Then we go to further left, then okay, we don't go to left. We do not increase the index because we can choose it unlimited number of times, right? Let's try it out. Right, current sum, we do have current sum. So first condition is very simple. If target minus current sum is less than candidates of index, you return. This is the base case. Then we start with our solution, right? Yeah. Cool. Next thing is, if this is not the case, what you do is you start add candidates of index, right? Then you go ahead and you do a solve for candidates with target with index and current sum plus candidates of index and ds, right? Yeah, you do this, and after that you come back from it, right? You add the index, go ahead, basically keep going on like this. You got 2, 3, 6, 7. Target is 7 in this case, right? Start from here. You get 2. Then you again go here, you get 4. Then you again go here, you get 6. Again go here, you get 8. Do nothing. You return. Then, alright. Over here you already have 6, right? Great. That's not how it works. That's not how it works. Let's see. Okay. Basically, 2, 6, 7. Right. First thing you receive is index 0. Index target. Next thing I need is current sum. The final list is list. Okay. Index is 0, target is 7, current sum is 0. List is this. Cool. This is what I get. I do get it as 7, 2, and 2. I further move ahead with 0, 7, 2. Now I get again 7, 4, 2, 2. Further move ahead with 0, 7, 4, 2, 2 का list, and over here what I'll get is 7, 6, 2, 2, 2. Further move ahead 0, 7, 4, 6, 2, 2. Right, this is what I currently have. Alright, the next thing is I get here, target is not 0. Get here, target minus current sum is less than candidates of index, which is basically 7 minus 6. You return from here. Basically, return from here. And you go on index 1 with target 7, 6, 2, 2. Again, return from here. You go back here. What you'll do now is basically it's something like solve candidates target. Alright, it is solve candidates. Will this work or will it throw an error? Okay. Alright. Alright, it failed every single case. That's the last one passed. Yeah. It's kind of a backtracking solution. Right, it is backtracking. So basically this is the base case. Cool, I agree on this. Alright. We'll do one thing, let us design this again. The thing is, if index candidates dot length, we'll return it. If candidates index is less than target and it's going some. Cool. You add it. So it becomes something like candidates, then you get target, then you get index. Then you get ds, and this dot add will be candidates of index. Alright. You have to make new combinations every time, right?
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve combination sum, and this is another problem from that blind 75 list. The link will be in the description, so we are doing one more problem and have very few problems from this list remaining. So we're given an array of distinct integers called candidates, and we're given a target integer called target, and we just want to return a list of all the unique combinations of candidates where all those numbers end up summing to the target value. And we're allowed to return those combinations in any order, and we're also allowed to use the same number from candidates multiple times, but we don't want to have duplicate combinations. For example, if 2, 2, 3 sums up to 7, right, that means 3, 2, 2. These are the exact same values, right? Just in a different order. These sum to 7 as well. So we don't want to add both of these combinations to the result because they're the exact same. So what we're saying is we want combinations. We don't want permutations that end up summing to the target value. So in this example, you can see that we are given these candidates and a target of 7, and we have 2 different ways that we can sum up to 7. Of course, 7 by itself does sum up to the target, and 2 occurrences of the 2 value and 1 occurrence of the 3 value added together are going to lead to 7 as well. So then we return these 2 combinations as our result. So I would say the difficult part about this problem is trying to figure out how to eliminate duplicate combinations, right? For example, if we just brute force it like a decision tree, so we have 4 different values we can choose each of them an unlimited number of times. What we can do is have 4 decisions in our decision tree, right? Like that might be the naive thing that you start with. So we would get 2, 3, 6, and 7, and then we'd basically continue that, right? On one path over here, we would find, okay, we found the 7, so we found the target, right? So we found one way that we can reach the target. So therefore, we don't need to continue down here because as we add more numbers, all of these values are going to be positive. So as we add more numbers, we're only going to get a sum larger than the target. So, I think it's kind of obvious why we don't continue down this path, right? But down here from the 6, let's try to continue, right? We can add a 2, so we get 6, 2. We could add a 3, so we get a 6, 3. We could add another 6, so we get 6, 6. And we could add a 7, where we get 6, 7. So notice how all of these are going to sum to a value greater than the target. So down this path, we never ended up reaching the target. We only went over the target. So we don't continue down any of these paths, right? But now let's continue down this path. So here we can get another 2. We can get a 3. We could get a 2, 6, but in that case, we would get 8, which goes over our target. We could also get a 7, 2, 7, but that also goes over our target. Now here's the part where we're going to end up getting duplicates. So I'm going to show you why this type of decision tree does not work. So here we could get a 3, for example, right? So we get 2, 2, 3. Now that sums to the target. Down this path, we could choose a 2. So we get 2, 3, 2. Notice how both of these end up summing to 7, but they're the exact same. They're just in a different order. We have 2 2s and a 3. Here we also have 2 2s and a 3. So we ended up getting the same one twice. So this works in finding the combinations, but we end up getting duplicate combinations. So what kind of decision tree can we try that gets us the result that we want, but does not have these duplicates? Let me show you how we're going to do that. Let's logically think about this. We know that we have one value in our candidates, 2, right? So we can try to get all combinations that include this 2 value, right? And see if any of those combinations leads us to the target value 7. Now, we could also, so then if we make a second decision over here, right, in this decision, we're definitely including at least 1, 2. Now, if we go down this path, we want to make sure that none of the combinations down this path ever match the combinations down this path. How can we guarantee that? Well, in this side, we said we're definitely including at least 1, 2. How about in this side, we don't include even a single 2? So basically, we skip 2. So here we're going to have an empty array because we skipped the 2, right? All we said is we were able to start from here, but we said, no, we're just not including a 2. We're just going to do combinations with these 3 values. That's going to guarantee that none of the combinations on both sides are going to be matching. And that's basically the logic that we're going to follow. So from here, remember, we can include multiple 2s if we want to, right? So one decision here could be including a second 2. So we get 2, 2. Now, this path is going to include all combinations that include at least 2 2s, right? But remember, our definition for this decision tree needs to be recursive, right? Because we don't want any of the combinations down this path to be the same as any of the combinations down this path. So what we said here is we're going to include 2 2s. How about down this path? We say that we're not including any more 2s now. What we're saying is we had 1, 2, but now we're done. We're skipping 2s. Now we're only going to use values from here. So that's the recursive thing, right? We're basically doing the same decision down here as we did up here. So here we're going to say we ended up skipping the 2, and we still only have one single 2. And so let's just continue to repeat that. So over here, we're going to add another 2. So we'll have 2, 2, 2. And over here, we'll say, okay, now we're done with 2s, right? We're going to keep ourselves at a limit of 2 occurrences of 2. And we're basically going to continue this logic until we get to our base case. So over here, you're going to see if we end up having 4 2s, we'll get a target of 8. So therefore, we went over our target value. So we're going to stop. But down here, right, this was our path where we said, okay, we're not going to include any more 2s in this path. So here we can make a decision. We can add a 3. So then we get 2, 2, 3. So we're continuing that recursive definition. And so notice how we have 2, 2, 3. That's 7. So we did find at least one combination. But remember down now, if we make a decision to the right, we want to make sure we don't have any duplicates from here. So in this side, we decided to add 1 3. How about down this path? We say we're done adding 3s. We're not even going to add a single extra 3. So this is going to remain as 2, 2. Now, I think it's pretty obvious that down here, since we're only allowed to add values 6 and 7, neither of these is going to end up leading to the target. If we add a 6, we'll get a total of 10. If we add a 7, we'll get a total of 11. Neither of these, both of these go over our target. So let's do so over here. We're not going to be adding any more 2s. So here we can add a 3. So we get 2, 3. And over here, we would skip adding 3s, right? So we're not going to add any more 3s. This is going to remain as 2. Now, down this path, at this point, we have a total of 5. So we're only allowed to add values 3, 6, or 7. All of those are going to end up leading to a total of greater than 7. So we won't be able to find any solutions down this path. I'm just skipping and drawing it out because we're kind of running out of room. Now, over here, what we said is we skipped 2. And since this path includes the one where we added a 3, so here we're not going to add any 3s. And so we're only allowed to choose 6 and 7. That's going to end up leading to totals of greater than, it's going to lead to either 8 or 9. Those are both greater than our target value. So here, we're not allowed to add any 2s because that's what this path was. So we can add a 3, or we can choose to skip 3 and add nothing. So here, since we're skipping 3, so we're only allowed to add 6s or 7. So here we can say, okay, get a 6. This path, we skip 6, so we're not allowed to add any 6s over here. And from over here, we'll say, okay, we can add a 7, which will give us the total 7, right? That's the target that we're looking for. So we did end up finding that. So that's our second solution that we found. Now, since this path is going to lead to combinations that do include a 7, this path cannot include a 7, but you notice how as we are continuing to go down right paths, what we're saying is, okay, we're basically removing the number of elements we can choose from, right? We're popping 2 initially over here. Then when we go down here, we're not allowing ourselves to choose 3. Over here, we can't choose 6. Then when we finally go down all the way over here, we're not even allowed to choose 7. So therefore, we have no choices left. So this is also going to be a base case because we ran out of elements. And the way we're going to be tracking which elements we can choose from is we're going to have a pointer. Let's call it I. And so initially it's going to be here, which means we can choose any of these elements. As we pop an element like this one, we'd end up taking our I pointer and shifting it over here, which tells us, okay, we can only choose these elements now. So that's the main main idea. This is going to be a recursion tree. Each recursion step, we can make 2 decisions, and it's pretty easy to code up once you can kind of understand this logic. Let me show you how to do that. By the way, the time complexity of this, you can see that our decision tree, we're making 2 decisions each time, so it's going to be 2 to the power. What's the height of our decision tree going to be? Well, each value in this is going to be positive. It's going to be at least 1, so the height of the decision tree can be at most whatever the target value we're trying to make it. So 2 to the power of t, where t is the target value. That's going to be the big O and big O time complexity of this problem. So we are going to do this recursively, but let's have our result variable, which is basically going to be global for the scope of this problem, because I'm going to define a depth first search function inside of our outer function. So a few variables we're going to pass into here. We do want to maintain which of the candidates we're still allowed to choose. So like I said, we're going to have a pointer I that's going to determine that. We're also going to have a current variable. We're only going to have a single occurrence of this. It's just going to be a list that tells us what values we have added so far to the current combination. For example, like we could have 2, we could have 2, 2, right? 2, 2, 3, etc., etc. And for the values in our current combination, we do want to have a total. So we want to be maintaining what's the total sum of those, because if it ever reaches our target sum, then we know we have found a solution. If we ever go over our target sum, that means we've reached the base case and we can't continue anymore. So in our DFS function, let's go ahead and define those base cases. We know the base case is if total ever ends up reaching target, that means we found the result. So what we're going to do is result.append. We want to append the actual combination, so we're going to append current. And since we're only maintaining a single variable list for current, we don't want to actually append current itself. We want to create a copy of it, because we're going to continue to use this current variable when we're doing the other combinations recursively. So we don't, because then we're going to be modifying it. So we just want to create a single copy before we actually add it to the result. And after we're done with that, we don't want to continue the rest of this function. So we're just going to go ahead and break out of it by returning. So that's the base case where we succeed. What's the base cases if we end up being impossible to find a combination? Well, one is going to be if I is out of bounds, meaning we can't choose any more candidates. So if I is greater than or equal to candidates, or our total ended up going over the target that we're trying to reach, that's a base case where we have to return immediately because we cannot find a combination then. Now for the actual recursive step, remember we have 2 decisions to make. We can choose to include the value at candidates of I, right? We can choose to include this value. So what are we going to do if we're including this value? Well, first of all, we're going to take our current values that are in our combination. We're going to take that candidate and go ahead and append it to our current combination, right? We're going to do that before we end up actually calling our DFS function. So we're going to call DFS, and what are we going to pass in? Well, we're including this candidate so we can potentially continue to include it, right? So what we're going to say for our index I that we're passing is I stays the same, right? We're not restricting which candidates we're allowed to choose from just yet. So I stays the same. We pass in current because we just updated it right now, so we can go ahead and pass it in. And the total did end up changing, so we took our current total and added this candidate to it, right? So we can go ahead and pass in total plus candidates of I. So let me delete this line because we're not doing anything with it. But yeah, so this is going to be that first decision where we do include the candidate. Now the next decision is going to be where we can't include it, but after we call this function, we want to clean up a little bit. We ended up adding this value to our current candidates, our current combination. So we want to go ahead and pop that before we go down the other decision. And so once we pop that, we can go down the other decision. That's if we're not ever going to include this candidate. So for the index, we're going to pass an I plus 1, indicating that we can't include any occurrence.
Got it. It's more like we can do it over here if cool, we do this right. Next thing we'll do is ds.remove. Sort size -1 and it just worked. Cool. So what we're doing is basically nothing much, but if target matches, we return it. If index passes the bounds, we return it. If the current sum is already greater than target, we return it. Then we consider the current value, we keep on adding it, right? Then we go back, we remove the value, we add another value. All right, cool. This is done. Yeah, I guess that's it for today. Thanks for watching. And yeah, that's it for today. Thanks for watching. I'll most probably continue the DS journey tomorrow. Cool. See you. Bye bye. Good night.